So welcome. This is the second in the lecture series you are to watch on Lewis dot structures and covalent bonding. We had considered the ionic case. Now we're going to consider the case of reacting nonmetals and nonmetals to produce compounds. So we see in the ionic case where we are combining metals and nonmetals, the metals give away electrons, the nonmetals pick them up, and we end up with ionic type compounds. Our first example was, of course, the sodium and the chlorine. Sodium loses the electron, the chlorine gains an electron. But suppose there isn't any sodium around. Suppose it is just chlorine. Well, chlorine still wants to get 8 electrons around it. But it, of course, is not going to be able to pull electrons off other chlorine atoms. They are all chemically the same. So instead, they're going to have to end up sharing the electrons. The chlorine puts in one, the other chlorine puts in one, and we get a pair of electrons between the two chlorines. And we talk about a covalent bond. A covalent bond is a pair of electrons shared between two atoms. And so the two chlorines each end up with 8 electrons around them by sharing the pair in the middle. On the other hand, this is significantly different from the ionic compounds. In the ionic compounds, the ions are attracted to each other, but they're not actually stuck together. They're each still the individual ions. In the molecules, the atoms are actually stuck together because they are both holding on to that pair of electrons. It's like holding hands with your girlfriend. Where one of you goes, the other one has to go, as long as you're holding hands together. And so we have molecules. The two chlorines are bonded together, and we get a chlorine molecule. Suppose instead of chlorine, we start with nitrogen, which is again one of the nonmetals. Each nitrogen starts with 5 valence electrons. And so each of the nitrogens puts in an electron, and we get a covalent bond between the two nitrogens. Now each of the nitrogens has 4 electrons to itself and a share of 2 more. Well, 4 and 2 is 6. It's not 8. It wants to get to 8. So now what is it going to do? Well, it has more electrons available. So what each of the nitrogen will do is actually add 1 more electron in between them. And we'll end up with a double bond. A double bond is 2 pairs of valence electrons shared between 2 atoms. So now they have 3 to themselves, and they are sharing 4. Well, 4 and 3 is 7. That's still not 8. So now what? Well, now what is simple? Each of the nitrogens puts in 1 more of their electrons to form a bond. And we end up with 3 pairs of electrons between each of the nitrogens. So we talk about a triple bond. A triple bond means there are 3 pairs of electrons shared between the 2 atoms. So now they are sharing 6, and each has 1 pair of electrons to itself. We talk about a lone pair of electrons. A lone pair of electrons is a pair of valence electrons that the atom is not using in bonding at the moment. And so each of the nitrogens has a lone pair. Up in the chlorine example, each of the chlorines had 3 lone pairs, along with its shared pair for its 8. And now we have to consider what happens if we bring 2 different nonmetals together. For example, bromine and phosphorus. Bromine starts with 7 valence electrons, phosphorus starts with 5. So the bromine puts in 1, phosphorus puts in 1, and we have a bond. The problem is, while the bromine with 3 lone pairs and a shared pair has its 8, the phosphorus is still short. It has 4 to itself and a share of 2, which is only 6. So if the phosphorus is going to get to its noble gas count, it's going to need more electrons. But the bromine is already satisfied, has no reason to put anything else in, and therefore is not going to add anything. So we have to bring up a second bromine atom. And the phosphorus puts in 1, and the bromine puts in 1, and we get a second covalent bond around the phosphorus. And again, the bromine is happy. It has its 3 lone pairs and its shared pair, so it's 8. But the phosphorus is still short. It has 4 shared electrons, but it only has 3 to itself. And again, 4 and 3 is only 7. And so we're going to have to bring up a third bromine. And it puts in 1, and the phosphorus puts in 1. And again, the bromine is happy. It has its 3 lone pairs to itself and the shared pair. And now, finally, the phosphorus is also satisfied. It's sharing 6 electrons, 3 bonding pairs, and still has its lone pair to itself for its 8. And so we get the compound, phosphorus tribromide. And this is important. This is where we start seeing stoichiometry appear. You can throw any quantity of phosphorus and bromine together you want, but the only compound you get out of it is phosphorus tribromide. If you start with a little phosphorus and a lot of bromine, you get a little phosphorus tribromide and have a lot of bromine left. If you start with a lot of phosphorus and a little bromine, you get a little phosphorus tribromide and have a lot of phosphorus left. Because this is the only combination of phosphorus and bromine atoms where all the atoms end up with a noble gas count. And so, like we said, we start seeing reaction ratios. So now we're going to consider a little more interesting case of reacting 2 nonmetals together. Suppose we bring together carbon and oxygen and have them react. The carbon starts out with 4 electrons, the oxygen starts out with 6. So the carbon puts in 1, the oxygen puts in 1, and we get a covalent bond. Unfortunately, at this point, nobody is happy. The carbon is sharing 2 and has 3 to itself, which is 5. The oxygen is sharing 2 and has 5 to itself, which is 7. So nobody has managed to make it to 8. That's okay. We have a solution. The carbon will put in a second one, and the oxygen will put in a second one, and we'll have a double bond. This wasn't the case in the previous example we considered, where it was phosphorus and bromine, because once the bromine had put in 1 electron and formed 1 bond, the bromine was happy and wasn't going to put anything more in than it had to. In this case, the oxygen was still short after forming 1 bond, and so it's happy to put in a second electron and form a second bond to the carbon. So now there's a double bond between the carbon and the oxygen. And the oxygen is doing fine. It has a share of 4 electrons it's sharing with its double bond to the carbon, and it has 2 lone pairs to itself. The carbon, on the other hand, is still not satisfied. It's sharing 4 with the oxygen, but it only has 2 to itself, and that's only 6. And again, in this case, the oxygen's happy, and so it's not going to put in anything more than it absolutely has to. So if the carbon is going to get satisfied, it's going to have to go looking elsewhere. So we have to bring up a second oxygen. And the second oxygen puts in 1, and the carbon puts in 1. And again, we get a covalent bond. But the carbon is still short. It's got a double bond for 4 and a single bond for 2, and 1 to itself. That's only 7. But again, the oxygen with a bond, a pair of electrons in the covalent bond, has 5 to itself, and so it only has 7. So the oxygen in this case is again also not satisfying. So again, the carbon puts in 1 more, the oxygen puts in 1 more. We get a double bond between the carbon and the second oxygen, and they're sharing 4. And now the second oxygen is happy. It's got a double bond to the carbon, 2 lone pairs to itself is its 8, and finally, the carbon, with a double bond to 1 oxygen is 4, and a double bond to the other oxygen is 4, has managed to get to its 8. And so again, we have a molecule of carbon dioxide. And that concludes today's discussion about bonding using Lewis dots and covalent bonding structures. There's going to be more to come, but that's going to be the next lecture in the series. Have a nice day, and I'll see you at the next time we get together.